Dear learners, those points were covered in part 1, and in this part, I'm going to start talking about the etiological classification. So if you remember the definition that was mentioned in the first part, there was a hint on the etiology. I want to reiterate it once more. So aniseikonia is defined as a condition of binocular vision in which there is a relative difference in the perceived size and or shape of images between eyes. And now here is the hint about the etiology, and it can arise from a variety of physiological, neurological, retinal, and optical causes. Here I highlighted the most important keywords in the definition, like binocular vision, relative difference, perceived size, and finally, as you see here, I wrote optical cause in red since it is a major cause for aniseikonia. And that's why this part will focus on this particular cause. And I will dive a little bit deep in optics today, so bear with me. Here again, the list of the causes. And now let's start with the optical cause. Regarding optical cause, or we can say optically induced aniseikonia, we generally mean the presence of anisometropia, which refers to any difference in the spherical equivalence between the two eyes. Anisometropia is often classified as either axial or refractive in origin. However, most patients with anisometropia have both axial and refractive differences between eyes, and it's rare to have purely axial or refractive anisometropia. In axial anisometropia, the overall refractive powers are the same in the two eyes, but axial lengths differ. And this is an ocular ultrasound, shows elongation of the axial lens and also posterior staphyloma. So this is a case of axial high myopia. And this is another case of myopic anisometropia, or we can say anasomyopia, and this is the IOL master. And as you can see here, the axial lens in the right eye is 28.43 millimeter, while in the left eye, the axial lens is 24.36 millimeter. So how about refractive anisometropia? In refractive anisometropia, on the other hand, the optical powers of the ocular refractive components, basically the cornea and lens, are different between eyes, but axial lengths are the same. So examples of refractive anisometropia, which is not uncommon, a case of unilateral aphakia when we have an anisometropic hypropia. And this is an ultrasound, and as you can see here, the absence of the human crystalline lens. Another example is asymmetric nuclear sclerosis that might cause myopic anisometropia. Also, we have pseudophakic surprises. So the type of anisometropia affects the theoretical sizes of retinal images, which is the physical size of the image projected onto the retina prior to any retinal or cortical visual processing. And for simplification, we will focus only on purely axial or purely refractive anisometropia. Here, you need to note the link between anisometropia and aniseikonia. Both anisometropia itself and the optical correction for anisometropia can cause aniseikonia. So in this slide, it shows that uncorrected axial ametropia, the retinal images are inherently different. So this is a schematic representation of the reduced eye when we have a principal plane, nodal point, and the principal axis. And here is an object represented in this arrow. And by using the ray tracing by only one ray from the top of this arrow, we can appreciate that the different retinal images here in axial ametropia. So this is the retinal plane for an ametropic eye with average axial length. And here is in axial hypropia, when we have smaller eyeball, you can see here smaller retinal image relative to the emmetropic image size. And here in axial myopia, you can see larger image size. So in summary, we have a larger retinal image size in axial myopia and a smaller retinal image size in axial hypropia without correction. And this incongruous retinal images produced by axial anisomotropia can result in inherent anatomic aniseikonia. So imagine now we have a case with +1 in the right eye and +4 in the left eye. Then the uncorrected retinal image in the more hyperopic eye would be smaller than the less emmetropic eye. So this kind of intraocular differences in axial length in conjunction with potential differences in photoreceptor density that I will mention in the next part can contribute to perceived image size differences. So how about the optical correction for anisomotropia? So as you know, there are three basic lines for optical correction. We have spectacles, then contact lenses, and finally refractive surgeries. These are the several options available for correction of any refractive error, starting with spectacles, through contact lenses, and finally surgery by means of refractive surgery. All are valid for correction of any refractive error, but should always be considered bearing in mind the knowledge, practice, and experience of ophthalmologists and the best optical and visual benefit for the patient. As you can see here, we have two patients who are wearing spectacles. So this one has anisometropia, in which the right eye has significant hypropia relative to the left eye. And I hope you can appreciate how the right eye looks a little bit bigger than the right eye because of the plus lens. The opposite is true for this case. So this patient has a high myopia in the left eye. And again, I think you can see how the left eye looks a little bit smaller than the right eye because this is a high minus lens. And you can see here the thick edge of this lens. And this is a picture of a pair of spectacles where the right lens here is minus 5.5. And you can see how many concentric rings at the edge of this lens, while the left lens is only minus 1.75. So in order to understand how optical correction in anisometropia can cause aniseikonia, we need to revise some optics terms. First, a reduced eye, which is a mathematical construct in which the eye is treated as a single ideal curved refractive surface, having one nodal point, one principal point, and two focal points. And then you need to know how to construct and how to calculate the size of retinal image in order to calculate what's so-called RSM, which is short for relative spectacle magnification. So we care about calculation of spectacle magnification since spectacles are the prototype for refractive error correction. There are two ways to construct the retinal image. First, we have to draw the reduced eye. So this is the principal axis, this is the principal plane, and this is the retinal plane, and this is the nodal point, and this one is the first focal point, or we can call it the anterior focal point. So the first way to draw the retinal image by drawing two rays. The first ray passing through the first focal point, undeviated, and by the refractive power of the eye, it will pass parallel to the principal axis. The second ray passing through the nodal point undeviated. And here is the retinal image. The second way is to draw an arrow, an object, and to draw only one ray passing through the nodal point undeviated. And here is the retinal image. Sometimes we use this schematic representation. In other situations, we may use this one to serve our purpose of demonstrating some concepts. Regarding spectacle magnifications, we have something called SM and RSM. SM is spectacle magnification, which is the ratio between the corrected and uncorrected image size, while the relative spectacle magnification is the ratio between the corrected ametropic image size and emmetropic image size. Clinically, it's more useful to compare the corrected ametropic image size with the emmetropic size, because most of the time we care about how the corrected ametropic image size would be relative to the emmetropic image size, especially if the other eye, the follow eye, is emmetropic. And when we calculate the RSM, we have three possibilities. The result of calculation is 1, we call it unity, or more than 1, which means that correct emmetropic image is larger than the emmetropic image size. Or we may have the RSM less than 1, which means the correct emmetropic image size is smaller than the emmetropic image size. And there are some factors that will affect the value of RSM. Basically, the type of anisometropia, is it axial or refractive? The position of the correcting lens, whether it is located at the first focal point or nearer to the first focal point, as in cases of contact lens wearer. And finally, the refractive error, whether it is myopia or hypropia. We have here a matrix of 8 possibilities and different results for the RSM, whether it is axial ametropia or refractive ametropia, and whether it is myopia or hypropia, and finally, whether the correcting lens at the first focal point or nearer than the first focal point. And the reference of all these possibilities were taken from the Elkington Clinical Optics. Now, I'm gonna show you each possibility one by one. So this is a schematic representation of retinal image construction in a metropic eye. The first possibility that we have axial myopia. So in order to draw a case of axial myopia, we should draw the retinal plane further behind the emmetropic retinal plane, as you see here. The spectacle lens here is located at the anterior focal point of the eye. So note here the anterior focal point of the eye in axial myopia is located at the same distance as in emmetropic eye. So by ray tracing, here the first ray passing through the anterior focal point and the optical center of the correcting lens undeviated, and by the refractive power of the eye, it will pass parallel to the principal axis. The second ray, when it hits the minus lens, it diverges a little bit, then passes through the nodal point undeviated. And here is the retinal image size in axial myopia. And as you can see, it is similar in size relative to the emmetropic image size. So the RSM here is unity, which means equals 1. And this is called Knapp's rule. The second possibility in cases of axial hypropia. So in case of axial hypropia, we must draw the retinal plane anterior to the retinal plane for emmetropic eye, because we have here small eyeball. And here the correcting plus lens is located at the first focal point or the anterior focal point of the eye. And by ray tracing, the first ray passing through the anterior focal point undeviated, and by the refraction of the eye, it will pass parallel to the principal axis. The second ray here, when it hits the plus lens, it converges and then passes through the nodal point undeviated. So again, the retinal image size in axial hypropia is similar to the emmetropic image size, and so the RSM is unity. So Knapp's rule applies also here. So what's Knapp's rule? In axial ametropia, if the correcting lens is placed at the anterior focal point or the first focal point of the eye, the image size is the same as in emmetropia. Having said this, there is some argument or controversy regarding Knapp's rule, and I will highlight this as I go deeper in the topic in the later parts. So how about the third possibility, when the correcting lens is located nearer than the anterior focal point? So in axial myopia, and here the correcting lens is located nearer than the first focal point, as in case of contact lens. So by ray tracing, this ray passing through the first focal point, and when it hits the minus lens, it diverges a little bit, and by the refractive power of the eye, it will passes parallel to the principal axis. And now this is the retinal image size, and as you see here, it is relatively bigger than imetropic image size. So the RSM here is more than 1. And this is just an example for the corrected myopic image, suppose it is 1, and the imetropic image is 0.8. So we have RSM of 1.25. In summary, in axial myopia, if the correcting lens is worn nearer to the eye than the anterior focal point, the image size is increased, and the relative spectacle magnification is therefore greater than unity. And that's why we say contact lenses in axial myopia have a magnifying effect. How about axial hypropia, when the correcting lens is nearer than the first focal point? By ray tracing, this ray, when it hits the plus lens, it converges, and by the refractive power of the eye, it will passes parallel to the principal axis, and here the retinal image size is minified. So the RSM here is less than 1. So if the convex lens in axial hypropia is placed nearer to the eye than the anterior focal point, the image size is decreased than in imetropia, and so the RSM is less than unity. And again, this is an example. Suppose the corrected hypropic image here is 0.25 and the imetropic image size is 1. So we have RSM of 0.25. So positive contact lenses give smaller image than the spectacles. So now we going to shift to refractive anisometropia. So in refractive myopia, you have to notice here, when we want to draw a refractive myopia, the retinal plane is placed as the same as the retinal plane for imetropic eye. However, the anterior focal point of myopic eye is nearer to the eye than for imetropic eye. So here the correcting lens is placed at the anterior focal point of myopic eye, and by ray tracing, this ray passing through the anterior focal point of myopic eye and the optical center passes undeviated, and by the refractive power of the eye, it will pass parallel to the principal axis. The second ray here, when it hits the minus lens, it diverges and then passes through the nodal point undeviated. So this is the corrected myopic image in refractive myopia. So the RSM, as you see here, is less than unity. We have smaller image. So the image here is diminished. How about refractive hypropia? So in refractive hypropia, again, the retinal plane is the same as the retinal plane for imetropic eye, but the anterior focal point of hypropic eye is further away from the eye than for imetropic eye. And here the correcting plus lens is placed at the anterior focal point of hypropic eye, and by ray tracing, this ray passes undeviated and then parallel to the principal axis. The second ray here will converge and then passes through the nodal point undeviated. And here the correct hypropic image is magnified. So that's why the RSM here is more than unity. And now, how about refractive ametropia when the correcting lens is nearer than the anterior focal point? So in refractive myopia, And now the correcting lens is nearer than the anterior focal point, and by ray tracing, this ray passes through the anterior focal point of myopic eye undeviated, and when it hits the minus lens, it diverges and then passes parallel to the principal axis. And you can see here the corrected myopic image here is almost the same as the isometropic retinal image. That's why the RSM here is approaches unity. The same applies for refractive hypropia. When the correcting plus lens is nearer than the anterior focal point as in contact lens, so this ray, when it passes through the anterior focal point undeviated, and when it hits the plus lens, it converges and then passes parallel to the principal axis. So again here, the RSM approaches in unity. That's why contact lenses is the preferable option for refractive anisometropia. And this is a common example of unilateral aphakia. When we have the RSM for spectacles in a range of 1.36 to 1.25. And why there is a range? Because it depends on the vertex distance, how far the spectacle lens away from the eye. So as you see here, typically the aphakic spectacle lens magnifies the retinal image about 25% larger than it would be in isometropic eye of the same lens. So when the RSM is 1.25, it means we have 25% magnification, whereas a contact lens magnifies about 10%, or some resources say 7%. I want you to note the different ways for documentation the magnification. So in RSM, we can use like this 1.10, which means 10% magnification. Then anterior chamber IOL, the magnification is only 3%. And the best option is having a posterior chamber IOL intraocular lens because the magnification would be 1%. So the most suitable option for correcting unilateral aphakia is having implantation of IOL in the posterior chamber. So let's do a quick recap here. This slide summarizes the previous slides, where we have a unity RSM in axial ametropia. So in axial ametropia, when the spectacle lens is located at the anterior focal point or the first focal point. And also we have RSM approaching unity in refractive ametropia when the correcting lens is located nearer than the first focal point. Whereas RSM is more than unity in axial myopia and less than unity in axial hypropia if the correcting lens is located nearer than the first focal point. And finally, those two possibilities are exactly the opposite of those two possibilities. Actually, it is more complicated because as mentioned earlier, we have mixed cases of refractive and axial. And also there is a controversy regarding the accuracy and validity of Knapp's rule in these two possibilities. With that, I end this part. We still have many to cover in the future. Thank you so much for watching this video until its very end, and I'll see you in the next part, which will be about the remaining causes of aniseikonia. Take care. Have a good day. Bye-bye.